Welcome Year 11s to this video on the conclusion for our topic on polynomials, which is the bisection method. If you're viewing this video, you need to have worked through the appendix in the Cambridge textbook. So assuming that you have done that, let's begin by introducing this method. So I'm going to start by looking at this function. It's a cubic polynomial. And the bisection method is a way to find roots. A root is a solution to the equation f of x equals 0. So this is a horrible cubic function, and I know I have some x-intercept here between 0 and 1, and the question is, what is the value of this root? Now, there are formulas for approaching cubic functions, and if you look online, those formulas are very, very complicated. As we go on in maths methods, we're going to meet functions where it's not even possible to write down a formula for the solution. And once we get into a situation like this, we need to use what are called numerical methods. A numerical method is a way of getting an approximate solution in decimals rather than a symbolic expression involving things such as square roots and pi. In the real world, functions are too complicated, so we rely on numerical methods a lot. And the bisection method is one of those numerical methods. Next year, you'll learn another method called Newton's method, but we haven't learned enough to understand that method just yet. So for now, we're going to use a very, very simple strategy for finding this point here. It involves what is called a sign change. The thing I want you to notice is, let's say I pick 2 points. Let's say I take x equals 0. What I want you to notice is this value is negative. However, if I look at the point x equals 1, I can see it's positive. And f is continuous. We haven't defined what it means for a function to be continuous just yet. For now, a simple definition will suffice. I'm going to say a function is continuous if I can draw it without lifting my pen. And if you're happy to accept that hand-wavy definition, you'll see that if I draw this curve between x equals 0 and x equals 1, at some point, to go from a negative value to a positive value, I have to have crossed the x-axis at some point. I don't know where, but I know it's happened somewhere. So if I can find 2 points, in this case, x equals 0 and x equals 1, where the sign of the function is different, I know that I have bracketed a root. So in this case, I have bracketed a root between 0 and 1. Can we do better? Yes, we can. And the bisection method is perhaps the simplest strategy of bracketing a root. Now that I've found 2 x values, which include a root, all I'm going to do is I'm going to halve that interval. So next I will check x equals a half. I don't know what that value is without the graph, but maybe I'll get a calculator out and find f of half. And then repeat the process. In this case, you can see from the graph that f of half is going to be negative, which means my next interval will be from half to 1. So let me make this more precise. You've got the calculations in your handout. F of half is negative And from our previous observation, f of 1 is positive. So previously we concluded that the root was between 0 and 1. And now we can conclude the root is between half and 1. And now we just rinse and repeat for as long as we want. You can do this as many iterations as you like. And then at that point, you're limited only by the processing power of your computer for however long you want to do this. So down at the bottom of this page, I've got some graphs for you. So when we apply the bisection method, we actually don't have the graph. We just have the values of the function. So imagine I just have these two dots here. At half, f is positive. At half, f is negative. At 1, f is positive. So based on these two calculations, I know the root is between 0.5 and 1. So now I repeat. This time I go from half to 1 and I find the midpoint, 0.75. And what I'm noticing is f of half is negative, f of 3/4 is positive, which means a sign change must have happened between those two values. So after another, what we call an iteration of the bisection method, we can see the root is between 0.5 and 0.75. And you'll notice now, start again with 0.5 and 0.75. Find the midpoint, which is 0.625. And we can see the sign change happens in the upper half, this time between 0.625 and 0.75. So that's the bisection method in a nutshell. At this point, I could actually let you go and just get you to try approximating roots to a function, and you'd have almost everything that you need to do the exercise. What I'm going to do over the next few minutes is describe the algorithm in detail and show you a pseudocode implementation of the bisection method. So turn the page and let's take a look at that. Alright, so first we'll begin with a statement of the algorithm. It's got some mathematical language. So there's a very strong assumption that we're making. We're saying the function is continuous. And I'm saying that at some endpoints, a and b, I think a picture is really helpful here. Let's say I've got a function and it can do all sorts of things. But the thing that I need to be sure of is that the function changes sign over this interval a to b. This part here tells us the function changes sign. And because it's continuous, it must have passed through 0 at some point. Don't worry too much about this. There exists some number c in this interval such that the function is equal to 0. I don't know what that is, but I'm going to approximate it using the bisection method. So this first statement is like a theory. It states that if the function changes sign, it must have passed through 0. And if it passes through 0, there must be a root. So now that we know that there's a root, let's define the bisection method. So you start with this interval a to b, and then you halve it for as long as you like. One of the things that we do, if we go further on with numerical methods, is we're going to stop either when we've done as many iterations as we want, or when the function evaluates to a number close to 0. So, for example, let's say I've got some number x, according to my bisection method, And let's say it's between negative 0.01 or positive 0.01. This could be an example of a criteria that we would use to terminate an algorithm which implements the bisection method. So either you specify the number of iterations or you say maybe I'm this close. So there's nothing special about the number 0.01. I can get as close as I want to. It just means I might need to run my computer program for longer. So this is what we would call a tolerance. Is a tolerance of 0.01. And if we find an x value using the bisection method, then this becomes our approximation for the roots. Okay, so here's our first description of the bisection method. And you'll notice it's written in pseudocode. So four inputs. These numbers x1 and x2 are what I've called a and b up here. It's just that I'm used to calling it x1 and x2 in my programming work. So define your interval, define your function f, define how many iterations you want to do. In the next version of the program, which is further down the page, we'll do a tolerance instead. And I've got a counter for the number of iterations that have been completed so far. So all I'm going to do is do a for loop from 1 to the number of iterations that I want. Could be 10, could be 100, whatever I like. So xm is my symbol for the midpoints. So this line calculates the midpoint. And then here's our if statement. So if f changes sign on the interval x1 to xm, then when I do my next iteration, I want to replace the upper bound of my interval with my previously calculated midpoints. Otherwise, do the opposite. Now, if it helps, what I'll do is I'll draw an interval, x1, x2, and xm. This part here says on the next iteration, we'll go from x1 to xm, whereas this part here says I'll go from xm to x2 at the next iteration. And after I'm done, I will do a simple print statement which will give me my approximation for the roots of f. Okay, that's a very simple implementation of the bisection method. Now, I can make one modification to do a tolerance. It's not really relevant to your calculations on the exam, because you won't be able to do a tolerance on your CAS calculator easily. But certainly for your overall understanding of programming with pseudocode and how this algorithm works, I think it's worth teaching. So what I need to do is include a flag or a variable that says, have I met the tolerance? If I have, I will change that flag to true, and that will allow me to exit this big while loop. You see, the thing with this program here is I don't know how many iterations I need. It's just that I know that I will stop once I've met the tolerance. So the program could go on for a while. A safeguard against this is to create another input where I specify the maximum number of iterations that I'm willing to do. If you don't do this, your program may never finish, and that's bad. So a good programming practice is to have this in as well. So the only thing that you need to know here is this line states that negative tolerance is less than the value of the function evaluated at my estimation for the root is between the negative and positive version of my tolerance, which is assumed to be positive. So before, I gave the example of the tolerance being 0.01, and so that would mean I'm happy for my function to be between minus 0.01 and positive 0.01. And once I've met the tolerance, I then exit the loop and print my estimation for the root. Otherwise, if I've exceeded the maximum number of iterations, I will exit the loop and just give a message to state that I wasn't able to do it. Now, I know this is really heavy, so I'm just going to make one more remark about this page, and then we'll do an example of the bisection method. The comment that I want to make about both programs on this page is the following. These programs assume that f changes sign over the interval x1, x2. If it doesn't, you have not met the conditions for the existence of a root, which the bisection method relies on. So if you wanted to, you could improve these programs further by specifying an if statement if the function changes sign. Then go through the loop and do the iterations of the bisection method. Because if you don't, you're going to do all these calculations, but you're not going to get anything because there's no root. So for example, imagine a situation where I've got this function, but I set up the bisection method between x1 and x2 as labeled here. There is no root here. This is bad. Okay, so the bisection method will fail here. Okay, so when you set up your program, you need to specify a bound, a bracket, that you know has a root. And the reason why we know there's no root here from the bisection point of view is it doesn't change sign. Okay, so just keep that in mind. Alright, that's enough theory. Let's do an example now. Okay, so this is something that is relevant for your tests now that I've hopefully given you a conceptual grounding of the bisection method. Let's now turn our attention to actually doing a calculation. So here's a polynomial. It is, after all, a chapter on polynomials. Here's the rule here. And you'll notice that if I do a quick graph sketch, which you're allowed to do because this is a tech-able question, there's 3 roots. So if I were to use the bisection method, I would need to actually do it 3 times to get all of the roots. And that's going to take a long time. So for this example, I'm just going to focus specifically on this root here between -2 and -1. And what we're going to do is we're going to do 5 iterations of the bisection method using a starting interval of -2 to -1. Why did I pick -2 to -1? No reason. It's just that it's obvious from the graph. Maybe it's obvious that I could start at -1.5. Maybe it's not. But let's keep things simple. And I'm going to do my calculations to 5 decimal places as well. Okay. So if you like, you could actually pause the video and see if you could carry out the calculation yourself. Maybe you've read the book already. Go ahead and try it yourself. But I'm happy to let you just watch the video as I do this now. So you'll notice that we've got a table here. And in past test papers, you'll notice that the table's been given to you to help you carry out this calculation. So right now we don't know whether the function p of x changes sign over the lower half or the upper half of the interval. So to decide that, we actually need to evaluate p at all 3 of these values. So I'm just going to use a calculator to do this. Not a fancy calculator by any means. So I've already defined the function. So f of -2, f of -1.5, and f of -1. So the numbers that come out are 19, 6, and -1. Okay, so where did the function change sign? It changed sign from a positive value to a negative value in the upper half of my brackets. So when I go to the next iteration, I'm going to use -1.5 as my lower bound and -1 as my upper bound. Now, you don't need to circle this because it's going to get really messy. But what I'm going to do is I'm going to highlight the parts of the table that tell me where a sign change has happened. Okay, so now I'm going to repeat this process. The halfway point between -1 and -1.5 is -1.25. If you're having trouble with that, feel free to use a calculator to get that result. Notice that I already know p of -1.5, so I don't need to calculate it again. Now I need to figure out p of -1.25, so let's do that. And the value I get is 1.84375. Okay, so now I ask the question, where did the function change sign? Well, it changed sign in the upper half again. So next, I'm going to do my next bracket from -1.25 to -1. The halfway point is -1.125. And I already know what p of -1.25 is. So I'll write that in. And now I need to evaluate the function at -1.125. And I get 0.26953. And look at that. The function changes sign again in the upper bracket. This doesn't always happen. Sometimes it will be the lower half. It'll alternate. But we'll see what happens as we continue working through this example. So by now, you're hopefully getting the picture here. Now, at some point you're going to need to find the midpoint using your calculator. I'm still able to do this mentally because I know these numbers, but the next one I won't be able to do mentally. I'd have to get a calculator out, so I'll show you what that looks like. So my next number is negative 1.0625. So we'll chuck that in, and we get negative 0.40186. Rounded to 5 decimal places, as I've asked in the question. Okay, now remember, every time I'm preparing for the next iteration of the bisection method, I'm asking the question, where in the bracket, where in the interval did the function change sign? The function did not change sign in the upper half this time because it was negative in the middle and negative at the right end. This time, the function changes sign in the lower half. So this time, I want negative 1.25 to be my lower bound and negative 1.0625 to be my upper bound. I can write in the values that I have from the last step. And now I need to find the midpoint of these two values. The easiest way to do this is to add the two values together and divide by 2. So negative 1.09375. And now what I'll do is I will evaluate the function at that point. So negative 0.07550 correct to 5 decimal places. And now at this point we stop. And now we've got to ask the question, what is my approximation for the root of p of x? Remember, if we go back to the graph, I expected the root to be between -1 and -2, probably closer to -1. Is that what we're seeing? Yeah, this value here is negative 1.09375 to 5 decimal places. It's approximately negative 1.1. And if you look at the scale of the graph, that looks about right. It's about 1/10 of the way between -1 and -2. Now, if you wanted to, you could keep going. It's worth going through the exercise of thinking, which way would I go? Well, again, we ask the question, where does it change? It changes sign between the midpoint and the lower half. So if I needed to, I'm not going to do it, but this would be my next step to keep going if I was going to set up the 6th iteration. Now, let's make a quick comment about the bisection method. This is very time consuming and it is tedious. In practice, if we didn't have a CAS calculator in this course, what we would do is we would write a computer program, pick whatever programming language you like, maybe it's Python, maybe it's C, whatever it is you want to use. And you could let the program run for as long as you needed it to, and you would bypass all of these tedious calculations. So that's what happens in practice. But for your assessment, you will need to not do this by hand. You'll do this with a calculator, but you'll notice that we're writing down the calculation. We're writing down the numbers by hand, rather than having the computer give it to us. So please ensure, as you're preparing for the assessments on polynomials, that you know how to fill out this table, and you have an understanding of the pseudocode, because we expect you to know how to carry out this algorithm, and we expect you to fill in a table, something like this. All right. So we're nearly done. The next two examples are more theoretical and discussion based rather than calculation based. So let's look at example 2 now. What I've got here is a polynomial. There's nothing special about these numbers, root 2 and root 3. The thing I want you to notice is that the root is between 1 and 2. It's about 1.4, and root 3 is approximately 1.7. And based on this rule, I'm expecting a turning point at root 2 and a stationary point of inflection at negative root 3. Notice the stationary point of inflection isn't actually at negative 2. It's at negative 1.7 because I've got the root 3 in that bracket. In some ways, this is a silly example because I've made up these numbers, but I've made up this example to illustrate a point. And what's the point I'm trying to make? The point is this. If I were to carry out the bisection method over here on the left between, say, these 2 points, that's going to give me good results because the polynomial changes sign on the left near the roots at negative root 3. But imagine a situation where I carried out the bisection method between x equals 1 and x equals 2. I need to ask the question now, is this going to give me good results? And feel free to pause the video and have a think about it. As I answer the question now, this is not going to give us good results because one of the assumptions that we make when using the bisection method is that the function changes sign, and it does not here. So it's going to fail to find that root. The root at x equals root 2 occurs at a turning point. All right. So the bisection method is very, very useful for the situations where it is applicable. It is not applicable in this situation. So if you've got a turning point on the x-axis and you're trying to find that root, you're going to need a different algorithm. All right, last example. Now, again, you're probably cluing up to what I'm trying to get at here. So let's start with a very, very rough sketch of this polynomial. I know that the polynomial is going to have roots at negative 2, positive 2, and positive 3. If I were to draw a rough sketch of the graph, maybe it'll look something like this. Okay, excuse my bad drawing. So negative 2, positive 2, and positive 3. And now imagine a situation where I apply the bisection method between minus 3 and positive 6. So, first question, does p of x change sign on this interval? Actually, yes, it does. P of negative 3 is negative. P of positive 6 is positive. So P does change sign. What's the problem? The problem is there are multiple roots here. There are 3 roots. So imagine a situation where I didn't know what these roots were, and I applied the bisection method over this large interval -3 to 6. If I apply the bisection method, it's only going to give me one of them, because it's going to get closer and closer and closer to a root where a sign change happens. If I have more than one in my interval, the bisection method is not going to pick that up. So suddenly, finding roots is not such a simple problem. How do I choose this interval to start with? I had to draw the graph. What happens if your function is really complicated? Finding roots is not that simple, and numerical methods is its own subject if you go to university. I'm giving you these examples to show you that this simple task of finding roots is actually not that easy. And while the strategy for the bisection method was really simple, and for that reason elegant, it's very easy to set up situations where it doesn't work. So here, there's multiple roots, and the bisection method is only going to give you one of those roots. You'll need a better algorithm to detect multiple roots, or you will need to set up a better interval that only contains one of those roots. Of course, in this case, we know what the roots are because the polynomial is really easy. The purpose is not to use the bisection method on a simple polynomial like this, but is to demonstrate that there might be issues in applying it when you need to work with more complicated functions, if that's what you're going to do down the track. If you take engineering or maths or physics, you'll probably take multiple classes on numerical methods in your time studying, because it's a great subject, but there's a lot of work involved as well. So that concludes my examples. So final reminder, please make sure that you can carry out the bisection method. I accidentally called it bisection algorithm there. And make sure that you can read pseudocode, because we expect you to be able to read it on the test. I want to finish with one final exhibit. Now, this is not examinable. In the handout, which you all have access to, I've given you an example of a Python program that implements the bisection method. And this has the same function that we used before, minus 2x cubed plus 3x squared plus 3x minus 3. You see these two asterisks here? That's the Python operator for the power. I gave you pseudocode before. Here is some real code in Python. And since you've done some work in Python, you should be able to read this program. This function here, absolute value, it forces a number to be positive. And I've defined a function with three parameters, x1, x2, and tolerance. And I've specified start at -2 and -1, use a tolerance of 0.01. And let's see what this program prints out. So you'll remember, after 5 iterations, we got the roots of -1.09375. That's correct. And in just 7 iterations, I've gotten a function evaluation that is smaller than 0.01. So I'm reasonably confident that this number, -1.10, is reasonably close to the root. If I wanted to, I could let the program run for longer. I've got it here. Here's the program in Python. I'll change the bisection tolerance. This is 10 to the power of -5. And you'll see in 19 iterations, I get a root of -1.1007. Pretty good. So it doesn't take too many calculations, but it's tedious. And that's why, in practice, we're not going to do this with a scientific calculator. We're going to do it with a computer program, because that's going to be much easier. If you've got something boring and repetitive and tedious, the best thing that you can do is to offload it to a computer because it's not going to complain. So, just this once, and just for this course, unfortunately, you will need to know how to fill out this table and how to read pseudocode. And once you finish maths methods and go off into further studies, if you need root methods, methods for finding roots, a computer is going to do the hard work for you. So I'll leave it to you to work through the exercise and look forward to seeing you next time. Thank you.